Your vehicle is lying to you right now. Deep inside your engine block, underneath the oil film and buried within the cylinder walls, a silent robbery is happening every single time you turn the key. It does not make a dramatic sound. It does not flash a warning on your dashboard. It does not announce itself until the damage is already done. But with every cold start, every rough acceleration, every mile under load, microscopic layers of metal are being stripped away through relentless friction. Power disappears so slowly that most drivers never notice it happening. Compression weakens, efficiency drops, response softens. The engine that once felt sharp, tight, and alive begins turning into a tired, expensive machine that no longer performs the way it was built to. And the most dangerous part is that people assume this is normal. They call it age, they call it mileage, they call it bad luck. But what if the real cause is something far more profitable? Ignorance? Because once you understand how much of modern engine wear is accepted as inevitable, the size of the business built around that wear becomes impossible to ignore. The global automotive repair economy has become a giant machine fueled by deterioration. Every worn cylinder wall, every weakened piston ring seal, every gradual loss of smoothness and power turns into another diagnostic bill, another workshop visit, another repair estimate that reaches into the thousands. Drivers are conditioned to believe that engines are supposed to slowly destroy themselves over time, that expensive wear is just part of ownership, and that the only answer is to keep paying for maintenance, parts, rebuilds, and eventually replacement. But hidden behind that system is an uncomfortable possibility. What if a large portion of that wear could have been reduced far earlier, far cheaper, and far more effectively than most people were ever told? That is where one of the most overlooked compounds in the world enters the story. Molybdenum disulfide. Not some flashy miracle liquid. Not a modern gimmick invented for internet ads. Not a fake bottle filled with empty promises. This is a real solid lubricant with a reputation that stretches far beyond car culture. In mechanical environments where pressure becomes extreme and ordinary lubrication starts to fail, this dark, slippery compound has long been valued for one brutal reason. It keeps metal from eating itself alive. The claim that makes it so explosive is not just that it lubricates, but that under the right conditions, it forms an ultra-low friction protective layer between moving metal surfaces, helping reduce the direct contact that causes gradual wear. And if that sounds too simple for something so powerful, that is exactly why most people never take it seriously. The fascination with this material did not begin in a glossy auto parts aisle. The story traces back to the raw mineral molybdenite, a dark metallic ore associated with molybdenum-bearing deposits and long recognized for its slippery feel. In Japan, where craftsmanship traditionally depended on reducing friction in tools, mechanisms, and moving assemblies, materials that improved smooth motion were valued long before modern automotive engineering gave them scientific names. Over time, practical observation always came first. If a surface moved more smoothly, lasted longer, and resisted grinding wear, craftsmen remembered it. They may not have explained it in the language of tribology, but they understood the result. Less drag, less heat, less damage, longer life. By the post-war industrial era, that practical understanding had collided with modern engineering. As Japanese automakers gained a global reputation for durability, efficiency, and disciplined maintenance systems, internal fleet servicing became a quiet battlefield of cost control and longevity. The real advantage was never just building a machine that ran well on day one. The real advantage was keeping it alive, tight and efficient for hundreds of thousands of kilometers with the least possible wear. That is why the idea of advanced friction control compounds became so compelling. In environments where engines faced constant use, every percentage point of reduced wear mattered. Every reduction in metal-to-metal contact translated into lower long-term failure rates, fewer breakdowns, and better retention of the engine's original feel. And this is where the silence around the subject begins to look suspicious. Because if a compound exists that can help reduce friction under severe pressure, preserve surface integrity, and slow the wear that gradually robs engines of their original performance, then why do so few ordinary drivers know anything meaningful about it? Why is the public conversation dominated by oil brands, premium filters, expensive additives with vague marketing language, and catastrophic repair bills, but not by the simple science of boundary lubrication? Why are people taught to obsess over symptoms after damage appears, instead of the mechanisms that cause the damage in the first place? The uncomfortable answer is that prevention is rarely as profitable as repair. A driver who delays wear delays bills. A machine that lasts longer starves replacement cycles. A simple low-cost solution is not exciting for an industry built on expensive consequences. So today we are pulling that hidden layer into the light. We are going to examine the science behind molybdenum disulfide, why it became so respected in high-stress mechanical systems, how it earned a near-mythic status among serious mechanics, and why so many drivers have never been taught what it actually does. We will unpack the friction, the wear, the loss of compression, and the gradual theft of performance happening inside engines everywhere. Then we will move beyond the theory and into the practical side. The simple driveway level protocol that made this compound legendary among people who cared less about marketing and more about keeping engines alive. Because once you see how the robbery works, you start to understand the real scandal. The destruction was never the mystery. The mystery is why nobody wanted you looking this closely in the first place. Now, to understand why this matters, you have to look at the one place most drivers never think about, the microscopic battlefield inside the engine, where oil stops being enough. People hear the words full synthetic and imagine a perfect protective shield floating between every moving part, as if the metal inside the engine is always safely cushioned and never truly touching anything. But that is not how a real engine lives under pressure. Inside an operating engine, components are moving with violent speed and crushing force. Piston rings scrape along cylinder walls thousands of times every minute. Cam lobes slam against followers. Bearings endure relentless load. And in those moments of peak stress, especially during cold starts, sudden acceleration, high heat, and heavy load, even the best premium synthetic oil cannot always maintain a complete, unbroken film thick enough to keep those metal surfaces fully separated. The protective layer compresses, thins out, and in the most heavily loaded points of contact, the separation begins to fail. That failure zone has a name in engineering, and once you understand it, you begin to see why so many engines slowly lose life even when they are well maintained. It is called boundary lubrication. This is the regime where the oil film is no longer thick enough to fully prevent surface contact, meaning the protection shifts from fluid separation to whatever chemical or physical film exists directly on the metal itself. In simple language, boundary lubrication is the moment where oil stops acting like a complete floating barrier and starts losing the fight against pressure. And that is the zone where the real damage begins. This is where microscopic asperities, tiny rough peaks on metal surfaces that look smooth to the human eye, start colliding with each other. This is where scuffing begins, where scratches are born, where the first stages of wear start cutting into the precision the engine was built with. The average driver never sees this battle, but the engine pays for it every day. And this is exactly where molybdenum disulfide enters the story as something fundamentally different from oil. Oil is a liquid. It flows, cools, carries contaminants, and reduces friction by creating separation. But molybdenum disulfide, MoS2, is not merely another liquid additive pretending to be smarter than the oil already in your crankcase. It is a solid crystalline compound with a structure that makes materials scientists, tribologists, and serious mechanical engineers pay attention for a reason. At the molecular level, MoS2 is built in stacked hexagonal sheets with a layer of molybdenum atoms positioned between two layers of sulfur atoms. That structure matters because the bonding inside each sheet is strong, while the attraction between those stacked sheets is weak. Under pressure, those layers shear and slide over one another with extraordinary ease. That means when brutal contact forces try to force raw metal surfaces into each other, MoS2 does not react like ordinary oil alone. Its layered crystal structure gives it the ability to keep sliding where fluid lubrication begins to collapse. That is the genius of the material. It does not win by replacing oil's entire job. It wins by protecting the exact zones where oil becomes vulnerable. When pressure climbs and the fluid film thins to the edge of failure, MoS2's lamellar structure helps create a low-shear interface that resists seizure, scuffing, and direct abrasive contact. In the harshest contact points, where two metal surfaces are desperate to grind into each other, those hexagonal layers behave almost like an ultra-thin deck of microscopic plates, slipping past one another instead of locking together. That is why this compound has earned such a powerful reputation in high-load lubrication science. It is not magic, it is material physics. The engine does not care about marketing words like advanced or premium. It responds to load, pressure, temperature, and friction. And in the boundary zone, MoS2 speaks the language that stressed metal actually understands. This is also where the term tribochemistry becomes important, because friction is not just a mechanical event. It can trigger chemical changes right at the contact surface. Under real operating conditions, anti-wear and friction-reducing compounds can react at the metal interface and help form protective films where the contact is most severe. In practical terms, that means MoS2 is valued not because it simply drifts through the oil as decoration, but because it can contribute to a low-friction protective presence exactly where wear risk is greatest, on the piston ring path, along loaded valve train contact zones, and on other surfaces living in repeated stress. The idea that the battle against wear is won only by the bulk oil itself is incomplete. In the most punishing regions of the engine, what matters is what remains on the surface when the oil film becomes dangerously thin. And once you look at the friction numbers, the entire story becomes easier to understand. Dry steel sliding on steel can produce a very high coefficient of friction, which is why unprotected metal contact destroys itself so quickly. Conventional lubrication dramatically lowers that friction, which is why oil is essential in the first place. But boundary friction is still a different battlefield from full film lubrication, because the metal surfaces are no longer perfectly separated everywhere that matters. That is where solid lubricants like MOS2 have drawn attention for decades. They are capable of pushing friction lower in extreme contact conditions, where ordinary fluid separation alone begins to fail. In practical terms, that means smoother contact, less dragging resistance, less heat concentration at the interface, and less long-term damage being carved into the surfaces that decide your engine's lifespan. So the real breakthrough here is not that synthetic oil is useless. Synthetic oil is absolutely necessary. It is one of the greatest protective technologies ever put into ordinary consumer machines. But it is not invincible, and that is the part most people were never taught. Oil does its best work when it can maintain separation. MOS2 earns its reputation when separation starts collapsing. One protects through film formation. The other becomes valuable at the edge of film failure. And once you understand that division, the whole mystery disappears. The hidden wear inside an engine is not caused because lubrication exists. It happens because lubrication has limits. The million-dollar question was never whether oil matters. It was what happens at the exact moment oil begins to lose control. That moment is boundary lubrication. That moment is where engines quietly age. And that moment is where this strange dark mineral built from sliding hexagonal layers becomes one of the most fascinating anti-wear weapons ever discovered. What turns this from a clever theory into something far more serious is the fact that molybdenum disulfide did not earn its reputation on internet forums or garage myths. It earned it in environments where failure is expensive, dangerous, and sometimes catastrophic. Engineers did not keep returning to MOS2 because it sounded exotic. They returned to it because, under conditions where ordinary lubrication can become unreliable, this material kept proving that it could reduce friction and protect metal surfaces under punishing load. Over time, that made it valuable in aerospace, industrial machinery, and other high-stress mechanical systems where smooth motion is not a luxury but a survival requirement. Once you realize that this dark, dusty compound was studied by serious tribologists and used in demanding applications long before most drivers ever heard its name, the entire tone of the conversation changes. This is no longer about a miracle cure. It is about whether ordinary people were ever taught the same wear prevention principles that elite engineering environments have respected for decades. The reason MOS2 became so important is simple. It thrives in the exact places where mechanical systems become brutal. NASA technical literature has described molybdenum disulfide as one of the most widely used solid lubricants, especially because of its ability to provide low shear strength films between contacting metal surfaces. In aerospace research, engineers observed that its friction performance on steel could become remarkably low when the material was properly applied. That matters because machines do not fail in marketing conditions. They fail under heat, stress, pressure, contamination, and repeated load. Those are the conditions where ordinary assumptions about lubrication begin to break down. And that is where MOS2 built its reputation, not as a replacement for every lubricant, but as a material that could keep surfaces alive when the contact zone became too severe to trust fluid film alone. That is also why fleet operators and high-mileage mechanics have always cared less about hype and more about math. For them, the question is never whether a product sounds impressive. The question is what happens after hundreds of thousands of kilometers, after endless heat cycles, after daily stop-and-go punishment, after all the invisible wear mechanisms have had years to do their damage. In that world, even a small reduction in friction can mean less surface fatigue, less gradual scuffing, less heat concentration, and a slower decline in compression-retaining surfaces over time. That is the kind of advantage that compounds quietly. It does not look dramatic in one afternoon. It looks dramatic after years of use, when one engine feels tired and another still feels tight, smooth, and mechanically disciplined, long after most people would expect deterioration to have won. And that is the real significance of MOS2. The story is not that one cheap compound magically makes metal immortal. The story is that wear is cumulative, friction is expensive, and surface protection matters far more than most drivers were ever taught. Once you understand that, you stop thinking like a consumer and start thinking like an engineer. You stop asking only what oil you poured in, and you start asking what happens at the exact moment lubrication reaches its limit. You stop treating engine wear as fate, and you start seeing it as a process that can be slowed, managed, and in some cases meaningfully reduced. That is why this material kept surviving every generation of skepticism. Not because it needed a myth to stay alive, but because the physics were strong enough to outlive the myth. Now comes the part people actually care about. What do you do with this information in the real world, in your own driveway, without turning a good idea into a dumb mistake? The first thing to understand is that there are two very different ways people talk about MOS2, and only one of them makes sense for most viewers. The risky path is trying to play chemist with raw technical powder. particle sizes, and homemade blending ratios. The SmartPath is using a reputable engine-safe product that already suspends molybdenum disulfide in a form designed for motor oil systems. That matters because the goal is not to dump mystery dust into an expensive engine and hope for magic. The goal is controlled application. Official product guidance from Liqui Moly says its MOS2 anti-friction engine treatment is self-mixing, can be added at any time, and uses one 300 ml can for roughly 3 to 6 liters of motor oil. Its related oil additive product recommends about a 3% to 5% dosage in engine oil. In other words, the safest move is not improvisation. It is following a proven product ratio exactly and resisting the temptation to improve the formula with guesswork. The second mistake people make is believing this has to be treated like some dramatic ritual. It does not. You do not need a laboratory setup, and you do not need to overcomplicate the process. What you do need is basic mechanical common sense. Start with an engine that has already reached normal operating temperature, because warm oil flows better and circulates additives more evenly than cold oil. Park the car safely on level ground, switch the engine off, give it a moment so you're not working around moving belts, fans, or splashing oil. Then shake the product thoroughly if the label says to do so, open the oil filler cap, and add only the amount recommended for your oil capacity in that specific product. After that, reinstall the cap and drive the vehicle normally so the treated oil can circulate through the system. The key point is discipline. Not too much, not too little, and not some internet-invented ratio that sounds more hardcore than the manufacturer's instructions. The protection story around MOS2 is about precision, not bravado. And this is where the warning section matters, because a lot of people ruin good advice by ignoring the exclusions. Liqui Moly explicitly states that some of its MOS2 engine additive products are not suitable for motorcycles with wet clutches, because friction characteristics matter in clutch packs that share oil with the engine. The company's own guidance distinguishes between standard engine use and wet clutch motorcycle use, and for motorcycle-specific applications, it gives separate dosage limits. That means the lazy habit of saying just pour it into anything with an engine is exactly how viewers get burned. If the machine uses a wet clutch, if the manual warns against friction modifiers, or if the product label excludes that application, stop right there. This is not the place to improvise. Follow the owner's manual and the product's official compatibility notes before adding anything. The final thing your viewer needs to hear is this: do not oversell what happens next. A good MOS2 treatment is not a movie scene where an old engine suddenly becomes new by the next traffic light. The believable benefit is more subtle and therefore more powerful. Reduced friction in loaded contact zones, smoother operation, and added wear protection over time when used correctly in a compatible engine. That is the credible promise, not instant resurrection, not a permanent miracle that makes oil changes irrelevant, not a fantasy where one treatment erases years of neglect. Real mechanical improvements usually feel like smoother running, quieter operation in some engines, and better protection against ongoing wear, especially when the product is used exactly as directed and paired with proper maintenance. That kind of claim is less flashy, but it has something internet myths usually do not: a chance of being true in the hands of a real driver. And that is the real twist in this whole story. The biggest secret is not that one bottle turns your engine immortal. The biggest secret is that most people have been trained to wait until wear becomes expensive before they take friction seriously at all. They will spend hours comparing fuel grades, arguing over brand names, or panicking over repair quotes, but almost nobody is taught to think about what is happening at the contact surface before damage compounds into a bill. That is why understanding this matters. Because once you start thinking like that, you stop acting like a helpless customer and start acting like someone who understands machines. So if your engine still runs, if it still pulls, if it still has life left in it, this is the moment to protect what remains instead of waiting for wear to cash its check. And in the next video, we are going even deeper into one of the most misunderstood corners of automotive maintenance: the low-cost injector and fuel system treatments that some drivers swear by, some mechanics hate, and almost nobody explains honestly.